Alright, as you can see here, this is case study 3. If we take a look at the final render first, this is the final render. If I temporarily switch between the original and final render, you can see the differences. Part 1 is 3D camera tracking. Part 2 is done externally inside Maya for 3D match moving, lighting and rendering. Part 3 is a simplified compositing process, more like a mini comp. Now let's dive into the part 1 section here. If I highlight the plate and press 1 to load it in the view 1 panel, you can see this is the original background plate. In this plate we have two movements. One is from the people, and obviously they're walking through the scene, and also some people standing here with some potential movements. Another movement is from the camera. The camera is moving. Because we are doing scene tracking, not object tracking, our concentration is on the static elements in the scene. We need to mask out these moving elements. That is why I used the roto node. If I double click it, I can clearly see we created a couple of really rough roto shapes to mask these people out during 3D camera tracking, and also some people standing behind the pillars and also behind the glass door here. Because these three people are moving, obviously, and we can see some reflections on the glass door. So the door must be masked out as well during 3D camera tracking. If I switch from RGB to alpha channel by pressing the letter A, these are the mattes we created for masking the moving elements in the scene. After the roto node, we have a lens distortion connected. This lens distortion is to remove lens distortion information from the scene. If we move to, for instance, 1150, we can see, especially from these two pillars, they are supposed to be straight, but in the shot we can see the barrel shape of these pillars. So before 3D camera tracking, we need to correct the lens distortion, remove the lens distortion information from the shot. In this project, I use a legacy lens distortion node, which can be accessed from the tool here. Then click Other, Update. After that, place your mouse cursor back to the node graph panel, press the Tab key so you can bring up the search slot type lens. Then from the drop-down menu, you can say Lens Distortion Transform. This is a new node, but the Lens Distortion capital L is the legacy Lens Distortion node. If I connect it to the roto node and double-click it, and so we can load the parameters in the Properties section. Go to the Line Analysis tab. If you want to remove lens distortion by using this node, under the Line Analysis tab, take the Drawing mode on. Then after that, we're going to draw a group of control points based on the existing shape of the pillars. For instance, you want to be accurate. For demonstration purposes, I'm going to move fast. Alright, then after drawing it, then right click, then you can see a yellow line is placed and followed the shape of the pillar. So I'm going to do this side for this pillar. Right click and to finish your operation. Then after that, click Analyze Lines tab. Then if we do a comparison between the original and after, and also if I temporarily hide the yellow lines by clicking the Hide Lines option here, before, after, we can clearly see the pillars are getting straight. This is what I did exactly in here in this node. We can clearly see overscan is created, extended beyond the boundary of this original plate. After lens distortion node, the next node is camera tracker. If we double click it, then load it to the properties panel. Under the camera trackers tab, we can see the mask input is set from none to source alpha because we do have, mats created in the alpha channel. Under the camera section here, camera motion is free camera, which is correct. Lens distortion, we don't have lens distortion for now. We removed the lens distortion already. And for focal length and frame back preset and film back size, we don't know this information at all. Okay, so we're going to leave everything as default. Switch back to the settings tab. Increase the number of features to 1000 and also take the refine feature locations. Then after that, go back to the camera trackers tab, then click the track button to start your 3D camera tracking process. Now, based on the configurations of your computers, it will take a couple of minutes. After the first tracking is finished, then click the solve button here. Now you can see some good tracking features, and the green ones are good, and also we have some red ones. That means we have tracking errors. Then after that, we're going to go to Auto Tracks tab and select these bottom 3 options. And from here, the solve error, we can say it's already good enough, 0.86. We're dealing with a full HD size plate, and the solve error is under than 1, which is pretty good already. But let's say if we can reduce these error numbers even further. Select those bottom 3 options. Down here, we have some sliders. We're going to tweak those sliders. You don't want to do it too harsh, otherwise you will see all the red errors. In this example, my concentration is on the ground. I want to keep all the good tracking features on the ground. Then after that, delete unsolved, yes, and delete rejected, yes. Immediately you can see the solve error went to 0.45, which is very good. Then after that, go back to the camera trackers tab. You want to update the solve. Click OK. That's your final error threshold, which is 0.44. Not too bad. For now is 0.44, but we can push this even harder. Delete unsolved. Delete rejected. Immediately you can see 0.37, which is pretty good. Click update to solve. I'm going to stop here and say this is a good number for the error, which is quite low, 0.37. After the tracking is finished, obviously you want to see the result in 3D. Place your mouse cursor inside the View 1 panel and press the Tab key so you can switch to Nuke's 3D system. If you are Maya user, you can change the navigation to match with Maya, not using the default Nuke navigation system. To do it, you can go to Preferences, Viewer Handle, and by default the 3D navigation is set to Nuke, but I switched to Maya because I'm a Maya user. After that, click OK. Now the rotation and dolly in and out and pan is exactly the same like what you do in Maya. Now you can see the 3D camera tracking result. That's the ground. If we see the grade inside Nuke as a ground, now we can clearly see halfway of these tracking features are underneath the ground. We want to bring up these features up and put them on the ground. Okay, now press the Tab key so we can go back to the 2D view. We're going to select some tracking features on the ground and right click and ground plane set to selected. After that, they turn to purple. That means I set this group of tracking features on the ground. Let's take a look at the result in the 3D system. If we press the Tab key now, and we are back to the 3D system inside Nuke. Now you can clearly see these purple dots are sitting on the grid. Also from the tracking features, we can kind of see this is the pillar on the left, and this is the pillar on the right, and also upstairs. And this is the glass door, which is masked. That is why you don't see any tracking features on it. Now, with the camera tracker node is still selected, if you go to the export section, then switch from camera to scene, click it. After the camera rig is generated, we can see that's the camera which is connected to the scene. And if I scrub through on the timeline, we can clearly see the camera is moving. If you double click the camera and go to uniform scale, decrease the size from 1 to, let's say, 0.1. And based on the scale of the scene, we can see the scale of the camera is more reasonable now. That's the camera movement. Okay, that's the indication of the camera movement. And that's the ground, and that's the pillar on the left, on the right, and that's the corridor. If you want, you can test if your camera tracking is accurate or not. We're gonna place a couple of geometries into the scene. Go to this little cube here, then 3D Classic, Geometry. You can use different geometries here. By default, it's gonna be huge, but if you press W, you can bring up the translation gizmo, E for rotation, R for scaling up and down. You can switch to different views, Z, X, C, V, go back to the perspective. If you want, you can switch on the light, so you can better visualize your geometries in the scene. Next, I'm gonna create a pillar on the left based on, those tracking features here. The pillar on the left is matched with the original background plate because later a CG cloud will be placed here and also the reflection will be on the glass door. So this side of the pillar should be precisely matched with the live action plate. With the geometries tested and the camera accurately tracked and also all the tracking features available to us, we used the right geo node to export these elements out. Double click the node. There are 3 options ticked: geometries, cameras, and point clouds. And the file format is FBX because the camera is animated. Okay, this is the setup for the 3D camera tracking data. This is the camera movement we saw in Nuke. In the outliner, we have a group. Open the group and Nuke camera, that's the Nuke camera. If I switch to a different viewport, you can see that's the camera we tracked in Nuke. All the keyframes are embedded. Then after that, tracking locators, they are all the tracking features actually. By default, these locators are looking huge. So we select all the locators, change the XYZ from default 1 to 0.01, so they look reasonable to us. And also, based on the tracking features, this is the glass door we created and later will be used for rendering purposes. The camera size is 2008 by 1130. This size is calculated initially in Nuke. If we go back to Nuke, original background plate 1920 by 1080. After removing the lens distortion from the live action plate, the actual plate is getting extended. We need to calculate this size and put it in Maya. And we can see numbers here, 1964 by 1105, X and Y. In the lower left corner, we also have X and Y numbers, 44, 25, extended from this point to here. So we need to add this number and plus 44 for x-axis, and also this number is y, xy, 1105 plus 25. To get the initial overscan size set up, click this clapperboard with the little gear to bring up the render settings. Then you can set up your initial size here, width and height, 2008 and 1130. That's the initial overscan. However, this size is not the final render size for the overscan plate. To calculate the final render overscan size, we can use a MayaML script. To do it, if you see this lower right corner, click it, we can bring up the script editor. In order to use this script, we need to first of all select the camera. That's the camera we tracked in Nuke. Go to File, Open Script, select the overscan now, click open. A little overscan calculator dialog window popped up. The target height, I'm going to add 100 pixels. After that, click calculate overscan. The new render width is 2186 and the height is 1230. So the width and height should be used in Nuke for setting up the final overscan background size. Now let's go back to Nuke to set it up. Now we are back to Nuke. After the lens distortion node connected reformat node, in the properties section here, output format we set to the width and height, which is calculated inside Maya here, 2085 by 1230. If we take a look at the reformat result, this is the final overscan size for setting up renders in Maya. So after the reformat node, use a write node to write this aspect ratio out as JPEG sequence. Then eventually this JPEG sequence will be exported from Nuke and imported into Maya as a reference. Now let's go back to Maya to see how these sequences are loaded in Maya. Now we are back to Maya. To import the final overscan background plates exported from Nuke to Maya, we need to select the camera first, then Ctrl A. Under the Image Plane Shape 1 tab, Image Name, and click this folder. Then under the 301 Library Shot Nuke Datas folder, overscan background and with correct aspect ratio indicated here. Highlight the first one, then click open. Then after that, this is only the first frame, but if you want to use the entire sequence, you need to tick the use image sequence here. If you quickly test it, everything is matched quite nicely. We have the testing geometries, and also we built up a ground. We have a measurement here, 295. Maya has different units. If you go to the lower right corner, click this little guy here. Under the settings, we use the default centimeter. That means nearly 3 meters. So how to get this measured? For instance, I'm scaling the entire scene to match the real-world scale. In this case, based on the scales of those pillars, we can calculate roughly they are around 3 meters high. To scale up your scenes, you can go to Create, Measure Tools, Distance Tool. Once the Distance tool is activated, for instance, if I want to measure the height of this cube, click the bottom and click the top. Now you can see it's roughly about 73 centimeter, in terms of the height of the cube. If I put this measurement into the group of the scene, if I want to scale up the entire scene, the numbers here updating in real time. Because the pillar is matched with the real-world reference image about 3 meters high, and the entire scene is matched to the real-world scale. Alright, now it is time to set up HDRI lighting. We're going to use Arnold Sky Dome Light. And this will create a sphere to cover all the scenes set up. With the sphere still selected, then go to its attribute editor. Color, click this checkerboard icon here. File, image name folder here. Navigate to the case study 3 project files folder. Library shot Maya data and unset HDRI. Then select the HDRI. Click open. If you still don't see HDRI image mapped on the sphere, press number 5 on your keyboard. In order to properly receive lights in this environment, because these geometries are sitting inside a building, we are supposed to see some, shadows cast by the pillars or, different elements in the environment. So we need to build up this environment. This is the environment we built up for this scene, matched really nicely for the key elements here and the pillars. we're doing it for testing purposes. But once we feel happy with the renders, we can switch to some other characters, or even animate those characters for your storytelling. This is the final render for testing purposes. We only rendered out the main character, which also received environment lighting and reflections and so on and so forth. Then eventually set up multipass renders. We're going to introduce multipass compositing in later chapters. This is more like an extension of the script 1 after 3D camera tracking and testing. This is the second script for integrating 3D clouds into the live action footage. So let's take a look at each of these sections. The first is background plate. Nothing fancy, this is exactly the same background plate. The second section is to integrate the CG clouds into the live action footage. We started with the shadow cast by the CG clouds, obviously reformatted. You can say that's the original size, which is 2185 by 1230. Reformat, go back to the full HD size, apply the lens distortion to the shadow, then again use a grade node through the mask input to grade this part of the ground. As you can see here, the shadow has been generated. For demonstration purposes, we only used 2 passes. The second pass is beauty pass. Again, reformat, lens distortion, and also use ivory green to apply the original film green to the CG clouds, then pre-mod. So this group of nodes is more like a sandwich. This is a pre-multiplied image. Before grading and film grain being applied, we need to unpre-multiply them. Then after that, pre-multiply them again. Then we can put the CG cloud on top of the live action footage. Now it's looking more interesting. However, to get a better integration between the CG parts and live action footage, it would be really nice if this part can be hidden behind the pillar, and also because of the glass door, we're supposed to see some reflections of the clouds on the door. So to do that, in section 3, we used camera projection to achieve this result. These 2 nodes are copied from previous operations. As you can see here, roto, lens distortion to remove lens distortion from the live action footage, 3D camera tracking. Then eventually we got something like this. We put the clouds onto a card. The clouds are not dramatically changing their shapes. We only need 1 frame to project this frame, flip it, then to create the reflection on the glass door. So we use a frame hold to hold the frame 1190, use the reformat node to flip it over. Then after that, a little bit of color grading, then put it on the card. As you can see here in the 3D system, it's piped into the scene refilmed by the camera. Then eventually we get something like this. This whole process was done without considering of lens distortion information. That is why we need to get the original lens distortion information applied to this reprojected CG cloud. Then after that, we can integrate these clouds on top of this result. You can see here. But we also see some overlapping issues. We only see a little bit reflection from this side, not from that side. Section 4 and 5 is to use a similar technique of 3D camera reprojection to bring them to the front. For instance, in section 4, the script 1 3D camera tracking, we created a testing pillar. You can use this pillar to create matte for this one here on the left. And to fine-tune the position, we also use a transform geo to move the position precisely matched with the live action plate. Then after that, get it reprojected with alpha embedded. We also used a roto node to roto this side to get a solid matte to cover this side of the pillar. We use exactly the same technique for the right hand side. this pillar here, and also a mat embedded in the alpha channel. After projection, we use a channel merge to merge both mats. The mat here is really important. It should be accurately matched with the live action footage. Then also apply the original lens distortion back to the mat. If I do a comparison before and after, you can clearly see this, curvature shape of both pillars. Then we use a copy node, then copy the mat to the plate. Then after that, pre-mod. Then we can put these two pillars on top of the result we created here previously. That's the final result.